The following program is part of Cable in the Classroom, a free service of the cable communications industry and your local cable company.
Hey, I got a little question for you. What is just about the most important thing on the planet? Okay, I'll give you a little hint. It's not the mall or the telephone. I'm talking about something so important that no living thing on Earth can live without it. Give up? Well, the answer also happens to be the subject today at the weather classroom. Air. And lots of it. Here on planet Earth, we live at the very bottom of an ocean of air. We call that ocean the atmosphere, and like all oceans, it's really deep. In fact, it's a lot deeper than any of the watery oceans that cover the surface of our planet. For ages, people have tried to figure out just how the atmosphere works. They've studied it from on the ground looking up, floated up into it with balloons and looked around. And now, we even study it with satellites high above the Earth looking down. Scientists and explorers have risked their lives to learn more about our atmosphere. So we figured the least we could do was send our own explorer, Brandon, out to seek high adventure on the sea of air.
Hi, welcome aboard.
Hey,
Here you go.
this will help with the seasickness, right?
Yep. And don't forget to wear plenty of sunscreen.
Thanks. Adventure on the high seas. Yeah, boy. That's what I'm all about. Adventure. Welcome aboard the good ship Western Union here in Key West, Florida. This place has been a haven for mariners and explorers. And since we're going to explore the ocean of air above us, somebody thought, hey, I've got a good idea. Let's put Brandon, who gets seasick, on a boat and do the show like the ancient mariners would. Which is seasick, I guess. But no matter, I'll be getting me sea legs soon. And besides, we've got a lot to cover, so let's get to it. For ages, explorers and scientists have tried to discover the atmosphere's secrets, using kites, hot air balloons, airplanes, rockets, satellites, and even lasers to probe its mysteries. What they found is that the Earth's atmosphere is a mass of gases and ever-changing clouds. It's also the main ingredient in making weather. As a matter of fact, some scientists call the atmosphere the weather machine.
The word atmosphere comes from the Greek words, meaning ball of air.
So what's the big deal about air? You can't even see it. And if you can't see it, taste it, or smell it, how do you know if it even exists? That's a good question. In the 1st century AD, a guy named Hero was wondering the same thing. He noticed that if you turn a container upside down and put it straight into water, the water can't go into the container. Why? Well, he figured it was because the container was full of air. But if you make a hole in the top, the water rushes in and the air is forced out. So there's your proof. Air really does exist. Okay, once people figured out that there really was such a thing as air, then they started trying to figure out what it was made of. Of the mix of gases that we call the atmosphere, about 4/5 is a gas called nitrogen. Nitrogen, or N2, is a very stable gas, so it doesn't react much with other atmospheric gases like oxygen and carbon dioxide. Carbon and oxygen compounds are used by plants, along with water. But nitrogen doesn't play well with others, and that's why most of the atmosphere is nitrogen. The total mass of the air in the atmosphere weighs an estimated 5.5 quadrillion metric tons. That's 55 followed by 14 zeros. Sounds like a lot, doesn't it? Guess again. That's only a millionth of the weight of our actual planet. And it's the Earth's gravity that keeps our thin little atmosphere from floating off into outer space. But I'm getting ahead of myself. And anyway, I've got to get ready to sail. So let's hook up with Jason, who's been doing a little traveling himself, up into the atmosphere, to talk to the experts about our sea of air.
Not that line, Odell.
Aye, aye, Captain.
This is NCAR, the National Center for Atmospheric Research here in the Rocky Mountains. No place better to study the atmosphere. Come on, let's go inside. Here at this mile-high site in Boulder, Colorado, the NCAR scientists gather data and make observations using satellites, weather balloons, and research aircraft. Then, they take all that information and bring it back in here and use powerful supercomputers to help them figure out what's going on up there.
Here at NCAR, the National Center for Atmospheric Research, we do a number of interesting things that have to do with weather and climate. We study the sun, we study the atmosphere itself and the motions therein, storms. We study the ocean, and we study the chemistry of the atmosphere and how all these things interact. We have to go where the weather is. For example, if we study thunderstorms, we'll go to a place like Oklahoma. If we want to study tropical squall lines, we'll go to places like the South Pacific or the tropical Atlantic or to the African continent. NCAR scientists study the weather and climate in a lot of different ways. We have aircraft, we have supercomputers, we have the High Altitude Observatory where they use a lot of data from satellites and telescopes that are in other parts of the world. The aircraft are used for a number of things. For example, we have a radar in the aircraft so we can fly close to thunderstorms and look at their interior structure. We also have instruments on the aircraft that measure the wind, temperature, moisture, turbulence, and so on. And if the storms aren't too strong, for example, over the ocean, they're not as strong as they are over land typically, we will fly through them. The atmosphere is the weather machine. The atmosphere is a mixture of gases constantly in motion. Those motions get their energy ultimately from the sun, and they take incredibly diverse forms, highs and lows that you see on the weather maps on television, hurricanes that you can see in satellites, tornadoes, thunderstorms, snowstorms. All of these things ultimately go back to the sun, how it heats up the atmosphere on Earth, and how the air moves. We need it for life. We breathe the atmosphere. Plants need the atmosphere. They take up carbon dioxide from the atmosphere. We take up oxygen from the atmosphere, and we couldn't live without it.
The atmosphere. We live at the bottom of it. We swim through it every day. We even breathe it 16 times a minute, and most of the time, we don't think about it or even know it's there. And by the way, where did it come from anyway? You'd think it's been there forever, but everything's got a beginning, and the atmosphere is no different. Our friend Dr. Jim St. John at the Georgia Institute of Technology gave us a little history lesson on our own sea of air.
Scientists generally believe that our solar system began as a large cloud of gas and dust in the Milky Way galaxy. Gravity caused this cloud to collapse upon itself. Most of the material went into the sun, and the rest became the planets. Now, when the Earth was formed, most of the heavier material became the Earth and the oceans, but there was an initial atmosphere which was composed of carbon dioxide and nitrogen. Now, when life forms first began to appear on the Earth, they began producing oxygen through photosynthesis. Now, this was originally suppressed by a reaction of oxygen with volcanic gases. However, over time, much of the material within the Earth began to oxidize, and the volcanoes began emitting less hydrogen and carbon monoxide, and this allowed the oxygen to build up to its current levels, where it exists in an equilibrium, where it is destroyed by volcanic gases, the weathering of rocks, and respiration, and is produced by photosynthesis. And it's been that way for about 2 billion years now.
Okay, now my favorite expert, Colin Marquis, is going to give us the rundown on the layers of the atmosphere. He is so smart.
Sarah, the atmosphere is actually really thin. If the Earth were the size of a beach ball, the atmosphere would only be about the thickness of a piece of paper. The lower part of the atmosphere, the lowest part of the atmosphere, is called the troposphere. And that's where all the weather that we're familiar with takes place. temperature tends to decrease as we head upward through the troposphere. Next comes the stratosphere. And in the stratosphere is where we find the protective ozone layer. The temperature increases as we head upward through the stratosphere. Above the stratosphere is the mesosphere. In the mesosphere, we find the coldest air in all of the atmosphere. The temperature tends to decrease with increasing height. Above the mesosphere is the thermosphere. Temperature turns around once again and actually increases with height. And this is the layer of the atmosphere where most of the meteors tend to burn up. And then finally we have the exosphere, and that's where the atmosphere is getting so thin it's literally merging with outer space. And that's about it.
See how smart he is? Time to get back to Earth though, and the well-traveled Jason.
We're at the Furnace Creek Inn in Death Valley, California. It's a great day, so we're gonna take a little field trip. Got the top down, got the sunscreen on. So let's go get the lowdown on this air pressure thing.
In order to understand air pressure, we have to understand the term pressure. We hear the term pressure all the time, and we know that pressure is a force or some type of push. And the molecules that make up our atmosphere, or the sea of air that we live in, actually have weight. And this weight exerts a force down on the earth, the ocean, the land, the trees, houses, even you and me. It exerts this downward force, and that is what air pressure is. It's this force that's exerted on us by the weight of these molecules. Air pressure is a very key component to the weather that we see every day, no matter where you live. And when we hear the term air pressure, usually meteorologists on TV, you hear them talk about low and high pressure. These are pressures that affect what we see. Usually around a low pressure area, we'll see different weather like thunderstorms or snowstorms, those kind of things. But around high pressure is kind of good because it will be sunny, it will not be as cloudy in most instances. Most of us live right around sea level, and we experience air pressure because there are a large number of molecules that are above us that are exerting a pressure or a force down on top of us. But as we go up in the atmosphere, the pressure decreases because the number of molecules also decreases. If we were to jump in our car and drive into the mountains or climb a mountain, our body would notice this decrease in pressure, and our bodies would try to equalize our internal pressure with the external pressure. And what we might feel is kind of like a popping in the ear or something like that. At the same time, if we're climbing a mountain, we need oxygen to do that. And at a higher elevation, there's lower pressure, a fewer number of molecules, and a fewer number of oxygen molecules. Therefore, our body would realize this very quickly. Our breaths would get faster and deeper, and we would really need to slow down.
Here we are, weather fans, the lowest point in the Western Hemisphere, Badwater Death Valley, 282 feet below sea level. Now, we're gonna go for a ride with our barometer here, which measures air pressure, and this bag of chips, and this bottle of water, up into these mountains, and see what happens when we go up into a sea of air. Come on. Okay, sea level, ground zero for altitude. And our barometer reads 29.76 inches of mercury. Let's keep going up and see what happens. Check this out. As we go up the mountain, the altitude starts to increase. Look at what the barometer's doing. It's getting lower. Let's keep going to the top. Here we are at the top of the mountain. The altitude is 5,475 feet. Our barometer reached 24.26. Moral to the story, as the altitude increases, the air pressure decreases. Let's hop back in the car and see what happened to my bag of chips and bottle of water. The air pressure inside the bag or the bottle haven't changed while it's gone down outside. So, they've blown up like balloons. Now, when your ears pop, while you're going up a mountain road, for instance. That's your body's way of adjusting to the drop in air pressure. But when you're on a plane, you're really high in the atmosphere, right? So do you think the air pressure drops drastically? Well, let's see. Oh, there you are. Okay, we're flying at about 35,000 feet above the ground. Air pressure should have dropped like a rock, right? Well, let's see what Mr. Barometer has to say about that. Nope. Pressure is about the same as if we were on maybe a small mountain. What's up with that? Well, the plane cabin is pressurized. They pump air in to keep the air pressure up, so we all stay comfy. But the real mystery is, how did they get the camera outside the plane?
Because we live at the bottom of a sea of air, we see the atmosphere behave much like the bottom of any sea, with swirling currents and everything. Now, the sun's heat is the origin of all the weather that happens in our atmosphere, because it causes air masses to warm and circulate. That movement creates differences in air pressure, and that makes wind. But there's all different kinds of wind. So let's check in with our own windbag, Brandon, and get the real scoop.
Explorers have sailed around the world on tall ships like this for generations. With pretty primitive instruments, they figured out the ocean currents and charted their course into the great unknown. Just as important as ocean currents, though, were the currents above the water. And if you wanted to get to where you were going on one of these ships, you had to know how the wind moved. The most predictable of the winds are what we still call today the prevailing winds.
Prevailing winds blow in the same direction most of the time. Check this out. The Earth rotates from west to east, and at the equator, it spins at 1,000 miles per hour. But at the poles, it doesn't turn at all. The difference in rotation speed causes air to be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This is called the Coriolis effect.
Trade winds are probably the most famous prevailing winds. They blow toward the equator from the northeast and southeast. When wind was the only power that moved ships around the world, trade and exploration moved along the paths of these trade winds. And because trade winds have basically the same path summer and winter, the sailors could predict which way these tall ships would go.
If you have local land features like a mountain range or a beach, and mix it with differences in air pressure or temperature, you have local wind. If you live in California, you've probably heard of the Santa Ana winds. Or if you're from the Rockies, you probably know of Chinooks. But wherever you live, wind is a major part of the weather machine.
Well, local winds are really any wind that occurs in a small area, what we would call a mesoscale area, because anything that, like a city or a mountain or even a lake or the ocean can cause winds to blow differently right in that area, and so we would call that a local wind. The sea breeze is a breeze that comes from the sea. Meteorologists like to talk about winds in the direction they come from. So a west wind is not a wind that's going toward the west, it's coming out of the west, it's from the west. And so a sea breeze is a wind that blows from the sea. And a sea breeze will occur on a clear sunny day when there's no other strong weather system around. The wind starts blowing in from the sea to replace the warm air that's rising over the land. The land warms more quickly and that air is rising, and the high pressure air out over the ocean moves in to replace it. So people flock to the beach to experience the nice cool weather there with the breeze coming in off the sea. Well, there's actually lots of strong local winds as well, and a strong local wind that lots of people have experienced are the kinds that blow near mountain ranges, and they're strong downslope windstorms. They occur in California and they're called Santa Anas. And all along the Rocky Mountains, they're frequently referred to as Chinooks. And these are actually wind storms that can reach over 100 miles per hour.
We know that wind helps make weather, and sometimes it can cause all kinds of trouble. Over the ages, people have combined their brain power with wind power and put wind to work.
Well,
here at the National Wind Technology Center, we do research on wind energy technology to improve wind turbines, like you see behind me here, to produce electricity that can be competitive with fossil fuels. The Wind Technology Center was built here along the Front Range of the Rocky Mountains in Colorado because of the excellent variation of winds that we experience here. I think you can see behind me the gap in the mountains. The winds funnel through there, and in the winter we often get winds over 100 miles an hour, which is excellent for testing wind turbines. Wind turbines have been used for years. They used to be called windmills. They were used to grind grain, pumped water for wells, or to hold the water back from the Netherlands, for instance. And more recently, they've been used all across America before there was electricity and large electricity grids. We're interested in using wind energy because it provides us an alternate source of electricity. It'll extend our fossil fuel usage well into the future. Wind will always blow. It's renewable. We don't have to worry about using it up. And I think that people are concerned about the environment and the future of our planet, and we have children, and we want to make sure that they have electricity uses for their future as well.
The upper regions of the atmosphere were a new frontier for 19th century meteorologists. They figured out that the air up there held the key to a more complete understanding of the behavior of our weather. So they perched their observatories as high as they could, on mountaintops. Others put hot air to the test, in balloons.
When airplanes were invented, explorers could move faster and higher than ever before. On April Fool's Day 1960, scientists loaded up a spacecraft with cameras and instruments and blasted TIROS-1 into orbit. For the first time, we got to see satellite pictures of the Earth, showing land masses and cloud covers. Now, we could get readings and observations from above the Earth's atmosphere.
Dry land. Oh, thank you. Thank you. Oh, I'm okay. We're home. So, that's it for my voyage. Atmospheric exploration has come a long way, and we're always learning more. And as long as there are explorers like all of you out there, who knows what we'll discover up there in the sea of air. Later.
Our atmosphere is amazing. We breathe it, we fly in it, we watch clouds go floating through it on a summer day. It even protects us from meteors and deadly radiation. It's billions of years in the making, and basically, it makes life worth living here on planet Earth. Kinda makes you wonder why we'd go on polluting it. But there's always hope. By studying and understanding the sky above us, explorers and scientists just like you will figure out how to return the favor and protect the sea of air that is our atmosphere. For the Weather Classroom, I'm Jocelyn. See you next time.